Okay. And then let me find my file. Oh, here we go. Okay, so this is the experiment that we're doing this week at home. Oh, really, look how I'm busy. Okay, so electrochemistry. So it's about batteries. So this is just to get you excited. Oh, look how old this was written. MP3 player. That's hilarious. You guys don't even know what that is, do you? Yeah, you need to update that. Okay, so this is really the key to your data analysis. Okay, so you're going to want to focus on this setup. So if you look at this setup, you're going to want to refer back to it constantly and use your units, and then you'll be able to do your calculations. So just keep going back to this. So if you look at the units and the way the units work out, we have a coulomb over a second. And then the seconds would cancel. If you had seconds per grams of copper, the seconds would cancel. And then ultimately your grams of copper would cancel with this grams of copper. This is from your periodic table. Okay, this one electron per 1.6 times 10 to the minus 19 coulombs is a constant. So you will be using that constant at some point. And you notice the coulombs would cancel. We're assuming the copper is going to copper plus 2. That's how we get the 2 electrons. That would be from the half reaction. So you would cancel this electron with this electron. This should say moles of copper atoms, and so the atoms would cancel. But then what you end up getting is the Avogadro's number, the one that you accidentally memorized, the 6.02 times 10 to the 23rd. So if you do all these calculations together, then, okay, then you would get, I hope that's admitting everyone, okay. Okay, then you would get this overall, Avogadro's number. So that's the goal of part B. Ultimately. Okay, part A is making a battery.
We don't need to write the procedures on.
Oh, we will talk about that.
Okay.
Okay, so, and I do feel bad because this is fun to actually make the battery. So I kind of feel bad that you guys can't do this because you probably don't have any zinc sulfate at home. And you probably don't have any copper foil. Yeah, because that was actually the fun part, was to make the battery. And we have this glass that we would use for the salt bridge, but you don't get to do that. Okay, so this part B is where you're going to do your data analysis. And that's to find the Avogadro's number. And then we won't be doing C because we don't get to design a battery. Okay, so you will be answering the pre-lab problems. And then you notice they've given you the shorthand notation. So you're going to want to make sure that you follow the shorthand notation like we discussed in the lecture in order to write the net ionic. And they've given you the half reactions. And then they're asking you to calculate the E of cell. Looks like the answers are all in the back on this. Oh, okay. So, and this is giving you some data. The amperes is the current, and then the time, and then the grams, and oh, are all the answers in the back? What the heck?
Only 1 through 4, not 5 to 8.
Oh, only half of them? Back in the day, we didn't have any answers to anything. Just saying. Okay. So, but if you look at those and you can do those, then that will help you to do the 5 through 8, because if you see that they're similar. So they're giving you the shorthand notation. They're asking you to calculate the E of cell. And if you look at number 7, that was similar to the other one. And so you could use those as a guideline. So that will help you. So yes, you're going to answer all of these. Okay, this data is just messy for me. It's neat in your lab archive. So it is given in your lab archives. But this is just me doodling. I didn't want to undoodle it. I got too lazy. Okay, so this is just showing you, you will have some data, and then you're going to have to calculate the other parts. And you're going to refer back to that equation, that the setup with the units and everything, to be able to get which parts you need to answer here. So you're just kind of answering it using the data that you're given here. You're going to answer the blanks that are not filled in. And again, we'll look at lab archives because I've given you the data neater there. And then you're going to do all of this. Okay, and then because you're not actually doing the experiment, then you won't be able to do this. Because you didn't get to see what happens. And then, of course, we're not doing the options either. Okay, so let's go look at the lab archives. Let me find it. Okay. And let's see, where's all my, got lots of stuff here. Oh, here we go. Okay. I apparently have logged out. Oh, okay. Okay, so let's see what notebook I'm in. I am in the master notebook. Okay, so in this experiment 32. Okay, here we go. Oh, I'm already on it. Okay.
This is our last lab, right? Or no?
Don't you have a labster? You have a labster next week?
Okay.
Yeah, this is your last in your lab archives.
Oh, okay.
So it's going to be worksheet style, no formal lab report. You've done enough formal lab reports. You've done more formal lab reports than any other chemistry classes at the college. So yeah, answer all the pre-lab. So here's your data neater. So here's your data for part A, and I just gave you the data for part B that you would get in the normal face-to-face classroom or lab room, and then you have to do the calculations one by one to get the answers. And you've got 2 runs, and then just omit.
So, Professor, we're not doing a third run?
No, I didn't have, it's all the same calculations. So I just gave you 2. And so there's a place for your pre-lab questions. So to answer, was it Carolyn? I don't know who else. Carolyn else? I don't know. So no, I'm not going to make you guys do the procedure this time. No introduction. You've got enough to do because we have a couple weeks left and you got play to do. And so you're really just doing the results in the discussion. So you notice no conclusion either.
Do you want us to put anything for experimental or no?
Well, it's up here. The experimental's up here. If you don't put it, I'm not concerned at this point.
Okay.
In the past, I was trying to get you to do it because that's what you would normally do. But you guys already know that, so. So I'm going to be looking for the pre-lab questions and the results and discussion. That's what I'm going to grade. And you all have the same data. Okay, so questions about your Marab experiment. Okay, so we do need to finish up the chapter. And so, where were we? Wait, I don't even know where we were. Did we finish this one with the iodide? Does anyone know where we were? Because I don't. Okay, let's get out. If you could please get out your lecture notes, let's figure out where we were.
I think we did not do number 3 right there.
Number 3?
Yeah.
Okay.
We finished parts 1 and 2, but we didn't do 3.
Oh, okay, thank you. Okay, so this one looks like it gives you a half reaction. Oh, it's a PV equals nRT. So it's giving you the liters, it's giving you the volume, it gave you the pressure. You had to change that to atmospheres. Okay, so first we had to find the moles before we could even do anything else. So I set up the PV equals nRT and I solve for moles. And then that gave me moles of oxygen. Okay, so here I'm seeing I got 4 electrons. That's how I got the 4 electrons per 1 mole of oxygen. And then this is Faraday's constant per 1 mole. And so you see how the units cancel out? And then my moles cancel out. And then I get coulombs. Okay. Okay, so any questions? Does anyone need more time copying it down? Okay, so I'm guessing you're done?
Yes.
Okay,
Yes.
yes, I have an assistant here. Oh, good, he's gonna sit down. Oh my God. Oh geez, he's knocking everything over. Okay. Okay, this is practice for you. This is looking at, oh, sorry, God. Let me go back up. Okay, so this is looking, oh, I went way down. Okay, so this is looking at a nice diagram and just trying to get an idea of the terminology and given the information. And so we're just answering questions. What constitutes an electric current in a wire as electrons moving? And a solution, you'd have ions present. And so this is a specific example where we're using zinc, we're using graphite, we're using zinc nitrate, and then it's bubbling chlorine gas into the solution. And it's a very nice picture or drawing of the salt bridge. And so it's answering the question, why must there be actual contact of the two solutions? That's to prevent a concentration gradient. And I put in the potential series for just the ones we're using. And then you would want to be able to write the half reaction at the negative electrode, the half reaction at the positive electrode. You notice the negative electrode is the one that's giving off the electrons. The positive electrode is the one that's accepting the electrons. Whoa. Yeah, something weird happened when I scanned, it looked like. This is a real old paper. It's like yellow. That's how old it is. I've had this so long. So you're just going to want to copy this in. Or copy it down or sketch it or something to just help you. And then this would be a voltmeter right here. You would have some kind of a device to measure. And this shows you what it would look like, that you'd have to attach the wires. You'd have to attach the alligator clips. Yeah, this just scanned weird. That is very strange. Hopefully you can still read it. Now, once you have the separate half reactions, then you would add them up and you would add the volts up. Okay, so there's the chloride going to chlorine. That's the one that, let's see, oh, okay. Okay, so we use this one. The zinc going to zinc +2, we use that one. And then the chloride going to chlorine was the one we had to flip, so we had to change the sign. And then we add them up. And that's how we got the 2.12 volts. So the concept for you is being able to sketch a cell. So in case you're asked multiple choice questions, that you could answer the questions. Okay, do you have any questions about our sketch, our labeling? Does anyone need more time copying it down? Okay, so this is more practice. So you can see you've got the aluminum piece of metal, you've got a lead piece of metal, and then you've got the labels for where the electrons are going. So if this one is losing electrons, that's why it's going to be the negative. And electrons are going through a voltmeter. And then if this one's gaining the electrons, that's why it's positive. And then your salt bridge would have like a little piece of cotton here. You notice what's happening here. See how this one's getting smaller? And then the electrons are going to this one, and this one's getting bigger because it's the lead ion is plating it and going to lead atom. Then you would want to do half reactions in order to answer these questions. So this particular worksheet asks some of the questions first before how do you do the half reactions. So I'll give you the answers and then we'll figure out why. So which is more easily oxidized? That would be aluminum. You'd want to do the half reactions first and reverse one of them, and then you could do the balanced equation. But that's the balanced equation. And then again, you'd want to do the half reactions, flip one of them, and then you could add the volts up, and that's how you would get number 3. And then again, you'd want to look at the half reactions, and that's how you could figure out the electron flow. And again, looking at the half reactions, that's how you get the direction of the positive ion flow. And again, looking at the half reactions, you could figure out which is decreasing in size and which is increasing in size. And again, looking at the half reactions, you would figure out that you're gaining aluminum ions and you're losing lead ions. This is a definition. The voltage is 0 when the reaction reaches equilibrium. So that's just by definition. Okay, so here's where you would do the half reactions to figure out the anode and the cathode. And again, the anode is by definition the oxidation. The cathode by definition is the reduction. So you want to do the half reactions first and then go back and answer all these questions. So number 11 and number 12 is what allows you to answer all the prior questions. I don't know why they didn't ask that first. You add up the volts, that's how you get the 1.53. You look at where the electrons are going, and you can see the electron flow. Okay, so we see the electrons, like here's our arrow, the electrons are losing from the aluminum, so that's why I drew it as the electron flow leaving the aluminum. And then if this half reaction is going towards aluminum plus 3, you're losing solid and you're gaining aluminum plus 3. The lead is gaining electrons, so that's why the electrons are going towards the lead. And you're gaining the lead solids. That's why I drew that extra lead going on to the solid piece of lead already there. So the aluminum is losing electrons. That's how you could tell it's the negative electrode. And then the other one's the positive electrode. So really the key is do 11 and 12, flip one of them because you want to get your largest positive number. And then answer all the other questions. Okay, any questions about this? I know your brains are pretty tired. Does anyone need more time copying it down or have questions?
No.
Okay, we have a spokesperson. Okay, this is all about terminology. So at this point, just copy this down and then later, when you have a fresh brain, then you can work it all out. So this is just a matter of learning the terms because these terms are really good for multiple choice questions. So I'll just give you time to copy that all down. This was supposed to be the fun part, but I think we're all too tired to have fun right now. Okay, does anyone need more time copying that down?
No.
Okay. Okay, and then there's the sentences. Okay, we're going to worry about this after your quiz. We don't need to worry about this yet because it's not going to be on your quiz. Because we're getting ready for your quiz next week. Okay, so let's go to them. Oh, this is was made for you by one of the students in the Wednesday class. So she made this for the students. She's really good. My son thought I was listening to a CD when I was listening to it. Okay, so where did I put that? Oh, blah, 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 yeah. Electrochem, blah, blah, blah. And let's go here. Okay, so we're gonna watch this. It's pretty short, I think. So this is part of us doing lab. Wait, how do I?
An electrochemical reaction is a process where electrons are transferred between two
Wait, how do I get this bigger? Oh my God.
substances, with one losing electrons and the other gaining them. When a substance loses electrons, we say that it has undergone oxidation or that it has been oxidized. When it gains electrons, we say that it has undergone reduction or has been reduced. To help you distinguish between the two, remember the phrase oil rig, which stands for oxidation is losing, reduction is gaining. Some electrochemical reactions occur spontaneously, which we can study in a galvanic cell. The galvanic cell has four main parts. First, there are two metal electrodes, each of which is immersed into different electrolyte solutions. The solutions consist of the ions needed for the half reactions, either the oxidation or reduction reaction, that occur at each electrode. The solutions are connected by a salt bridge, which enables the flow of ions and maintains the charge neutrality of the solutions. The electrodes are connected by an external circuit, which the electrons travel through during the reaction. The anode is the electrode that gives up electrons in the reaction or is oxidized. The cathode is the electrode that gains electrons and is reduced. To help you distinguish between these two labels, remember the phrase red cat, since reduction occurs at the cathode. So how do we know which metal acts as the anode and which acts as the cathode? We can use the standard electrode potential of the metal, which is a measure of the metal's tendency to lose electrons. A more negative electrode potential means that the metal has a higher tendency to lose electrons. Electrons always flow from the metal with the lower standard potential to the metal with the greater standard potential. In a galvanic cell, electrons flow from the anode to the cathode. Thus, the anode is the metal with the lower standard potential, and the cathode is the metal with the higher standard potential. As the electrons travel between the two electrodes, an electric potential is measured. The magnitude of the voltage produced is equal to the standard potential of the cathode minus the standard potential of the anode. So if two metals with similar standard electrode potentials are used in the galvanic cell, like lead and tin, for example, the magnitude of voltage produced will be low. If the metals have different standard potentials, like silver and magnesium, the voltage produced will be high. In this lab, you will construct a galvanic cell using two metal electrodes and measure the potential produced as the oxidation and reduction reactions occur. You'll then identify unknown metal electrodes using known standard potentials and determine the magnitude of the voltage produced.
Okay, well, that's kind of like the lab that you're not going to do because we're all at home. And my YouTube video stuff. Okay. And let's see, what else do I want? Okay, let me go back. Edit. Okay, maybe I'll do that later. I got a cat sitting on the desk. Okay, so let me explain what's going to happen here. Taking a long time. Okay. Here we go. Okay, so normally I would put you guys in breakout rooms and we would go over those clicker questions. But what I'm going to do, because I think your brains are kind of like your brains need a rest, I can't put this up on the, I can't put this in the modules because it's not ADA compliant. But I believe I can send this to you as an attachment and an announcement. Did you follow that? Okay, so I'll put the clicker questions in the module when I don't have a cat taking up 16 pounds on my desk. But then what I'm going to do is I'm going to send you the answers that I've done. Oh, the cat's moving. Okay. I'm going to send you the answers in an announcement as an attachment because that should not affect the ADA compliance of the modules. Did you follow that?
Yes.
Okay. Yeah, because to me, at this point, there would be no benefit trying to put you in breakout rooms when you just took a major exam. So that's the plan. I'll put the clicker questions in the module because that is ADA, those are ADA compliant. But then when I added the slides, I didn't consider ADA compliance. So I can send these to you as a file in an announcement. And then that should work. And I added slides to explain each answer. So that's what we're going to do. But actually, since I'm recording this, I just realized I can just go ahead and do this also because it will be on the recording. And then you could go look at the recording too. Oh, that's pretty smart. Okay, so I will put the clicker questions in the module. And then I am recording this and then I'll upload this to my YouTube channel. And so then you could have two ways of looking at the answers. So ideally, you would want to practice or try to do the clicker questions yourself. And then you've got two ways to check the answers. It'll be on my YouTube channel. And then also I will send you an attachment and an announcement. So I'm just going to go ahead and go through these. So maybe just don't look at them. So then you could, well, you're going to forget by then anyway. So I'm just going to go through these slowly so that they're going to be on the video. So some of these just, the answers are because of definitions. But I will definitely send you an announcement. I guess you can know all the answers now, aren't you? That's fine. So maybe just give yourself some time to forget that you've already seen the answers. And then you're definitely going to want to work them out because you do have a quiz next week. And these are also on your final part 2. Oh, I guess I didn't put a slide in there. You're going to have to review your oxidation numbers for sure because you need to know them for this chapter. You're going to want to be able to do the half reactions because a lot of these questions are doing the half reactions and you can tell what's happening. A lot of these are just definitions. A lot of these also you have to be able to interpret the reduction potential values and what they mean. So this was the idea of applying the electrolysis. In this particular one, you would do an experiment and you would find chlorine gas. And that's how you would know what's happening at the anode. Okay, this is, if you look at the volts, if you put a piece of copper in there, you'd have negative volts, and then the zinc would be negative volts. And if you overall get negative volts, then nothing's going to happen, no reaction. So if you add up these volts, you end up getting negative volts, so no reaction. This is in your book. You had to actually read your book. It was somewhere in the words. Oh, yeah, this is information that I am giving, like extra information. And this was the one where you find it's in the car. Oh, yeah, this is like another name for this cell. And then that's a fuel cell. So these are all from your books, your book, the idea of the names of these cells. And this was doing the equation or doing the calculations and making sure you're using your units. And so this was just setting it up so that the units cancel and give you what you want. You're going to want to have the time in seconds. Ooh. I left my seconds out. Yeah, 1 coulomb is 1 amp second. I accidentally left my seconds out. Okay, so I will send this as an announcement. It's also going to be on this video I'm making. I'll put on my YouTube channel. And I think you have done enough for the day. So now you can go do your laboratory. Okay, I think we're good on that. Okay. Okay, so now you are ready to go do your laboratory.